So definitions of acids and bases. When we talked about nomenclature, we talked about how acids have the word acid in their name, and in their formula they start with H, and that's how we learn to recognize them. Well, scientists need a little more specific definition than that. How did we decide what gets named as an acid? Well, there's a couple of different definitions, and we're going to look at two of them. One is the Arrhenius definition, and Arrhenius was a scientist who worked with these things. This definition is that an acid is something that produces hydrogen ions in aqueous solution. So we look at HCl. HCl is a covalent compound. It's two nonmetals. This is not an ionic compound. But when we dissolve it in water, when we put it into water, it produces hydrogen ions. It ionizes. And so this is an Arrhenius acid because when you put it into water, it forms hydrogen ions. And that's the definition of an Arrhenius acid. Those hydrogen ions are highly reactive. Let's think about a hydrogen atom. How many protons does a hydrogen atom have? One. How many electrons? One. So when it loses an electron to become a positive ion, how many electrons are left? None. All that's left is a proton. The most common isotope of hydrogen doesn't even have any neutrons. So a hydrogen ion is a bare proton. It is very, very reactive. I think of this hydrogen ion as being a little bit like a very young baby. You do not see young babies just out in public by themselves, do you? They're always accompanied by someone. Someone's taking care of them, carrying them around because they can't walk. That's how I think of this hydrogen ion. He's too small to be out by himself. So what happens is the hydrogen ion gets a ride on the water molecule. The water molecule has these two lone pairs of electrons, and it can share a lone pair with this poor hydrogen ion who has no electrons and is very, very unhappy. Remember when we talked about Lewis theory and bonding, hydrogen wants a duet, two electrons. So if this hydrogen ion just jumps onto this water molecule, now the hydrogen ion has a duet of electrons and it's happy. The oxygen's still happy. Overall, this now is an ion with a +1 charge because that hydrogen ion was deficient in an electron. So this highly reactive hydrogen ion bonds to the water molecule, forming this. This, of course, has a name. It's called the hydronium ion, H3O+. So we put an acid in water, it forms hydrogen ions, but those hydrogen ions don't stay by themselves. They leave the chlorine and they jump onto a water molecule and form hydronium ions. Now, what's confusing, and I wish I could do away with this, but I can't, chemists often use H+ aqueous and H3O+ aqueous interchangeably to refer to the hydronium ion. It really is a hydronium ion. There are no H+ aqueous ions. They are all bonded to a water molecule. They can come unbonded and do other stuff, but they're all like this. This arrow is not double-headed. This reaction goes completely this way. There's no hydrogen ions. They're all hydronium ions. So why do we even do this? It makes the equation simpler. And we understand H+ aqueous. Oh, it's swimming in water. It's going to ride piggyback on one of the water molecules. So H+, H3O+ mean the same thing. And I know that's a little confusing. When we write the molecular formula for an acid, we generally write the ionizable hydrogen first, the acidic hydrogen. So formic acid is HCHO2. So this hydrogen is the one that is ionizable. This is the one that comes off as a hydrogen ion and then goes and jumps on a water molecule. This other hydrogen doesn't do that. So here is a structural formula. Here we've got this carbon double bonded to an oxygen, single bonded to this hydrogen, then we have a bond to the oxygen, and here's another hydrogen. It's this hydrogen that comes off. Not all of the hydrogens in an acid can come off as ions. And at this level, there's no understanding that for you. You just have to believe me. So that was the Arrhenius definition of an acid. The Arrhenius definition of a base is something that produces hydroxide ions in aqueous solution. So something like sodium hydroxide. This is an ionic compound of sodium ions and hydroxide ions. It is soluble in water. So when we put sodium hydroxide in water, the ions separate and we have sodium ions and hydroxide ions. Hydroxide ions are produced, therefore this is an Arrhenius base. We learned in a previous chapter to recognize bases as being metal hydroxides. Any soluble metal hydroxide, even if it's only a tiny bit soluble, will produce hydroxide ions. You need to be careful though, molecular compounds sometimes have OH groups also. This is methanol, CH3OH, and you might see the OH and think, oh, that's a base. Oh, 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 that's a base. But this part coming before the OH is not a metal. It's CH3. This is a molecular compound, and it does not form hydroxide ions in solution. It's not a base. If we have hydrogen ions and hydroxide ions present in the same aqueous solution, they can react with each other and form water molecules. This is the net ionic equation for many acid-base reactions. So that's all really nice and everything, but there are some substances that act like bases. They'll neutralize acids even though they don't have hydroxide ions in their formula at all. They have no oxygen in them. An example of that is ammonia. And the Arrhenius definition also does not apply to non-aqueous solvents. We're not going to talk about those, but that is an important part of chemistry, and the Arrhenius definition doesn't work there. So we have to look at another definition. This was there were two scientists that came up with this, Brønsted and Lowry, and so it's called the Brensted-Lowry definition. This defines acids and bases in terms of protons being accepted or donated. So an acid is a proton donor, a base is a proton acceptor. A proton is a hydrogen ion. So we are talking about hydrogen ions. But now instead of saying that an acid is something that produces hydrogen ions in solution, we're saying it's something that donates hydrogen ions. A base, instead of something that produces hydroxide ions, is something that accepts hydrogen ions, accepts protons. And this applies to a lot wider range. It focuses on the hydrogen ions, the protons, in the acid-base reaction. So HCl is still an acid under this Brønsted-Lowry definition. When we put hydrogen chloride or hydrochloric acid and put it into water, there's actually a chemical reaction that occurs. The HCl donates its hydrogen ion to the water molecule, forming this hydronium ion. And then what's left is the chloride ion. Any questions about that? Looking at it this way, this more clearly accounts for what's actually happening. A hydrogen ion is not being set free from the HCl. The hydrogen ion, the proton, is being transferred from the HCl to the water molecule. So I said I think of those protons or those hydrogen ions as being like babies, right? So here, This is the parent with the baby, and we're transferring the baby to the babysitter. So now this water molecule is hanging on to the baby, so the parent can go off and do something else. Any questions? So the Brensted-Lowry definition works really well with bases like ammonia. If you just look at ammonia, NH3, you wouldn't necessarily think that that's a base. It doesn't have any hydroxide in it. How can it form hydroxide ions in solution? How can it act as a base? How can it neutralize an acid? Well, it is a base because it accepts protons from the water molecule. So here we have ammonia, and here we have water. The water can donate one of its hydrogens as an ion to the ammonia, and so now we have NH4+. This is the base. It accepts the proton from the water. The base is like the babysitter. They both start with B. The babysitter accepts the baby. I'll hold on to the baby for you. Okay? So this NH3 does produce hydroxide ions in solution, but not in the same way that sodium hydroxide does. It does so by accepting a proton from the water, and when we take a proton away from the water, what we have left is hydroxide ion. Acids and bases always occur together. So if you think of the baby again, the parent's holding the baby. The parent doesn't just toss the baby into the bushes. The parent hands the baby to the babysitter. There has to be a babysitter to hand it to. If there's an acid donating a proton, there has to be a base accepting the proton. And in order for the base to accept a proton, there has to be an acid to give it up. In order for the babysitter to have a child to babysit, there has to be a parent to give them the baby. Does that make sense? So the acid and the base have to be together. So here what we see is HCl is acting as an acid. It donates its proton to the water. The water here is acting as a base. It accepted the proton. It's babysitting the H+. When ammonia is in water, the ammonia acts as the base. It accepts a proton from the water. Here's the ammonia holding the proton, the hydrogen ion. So here, ammonia is the base. Water's acting as an acid. Water is pretty cool stuff. It can act as an acid or a base. And we have a word for that. Of course we have a word for that. We've got a word for everything, don't we? Amphoteric. An amphoteric substance is one that can act as an acid or a base, depending on the situation, accepting or donating a proton. You might think of water as being like a babysitter who has a child of her own. So she can have someone else babysit her child, or she still has her child, but she can also take another baby and watch him. Okay, because it is possible for a woman to watch 2 children at once. You can actually watch way more than that. And this word is, again, with the prefixes, right? Ampho. Where do amphibians live? They live in the water and on the land. They're comfortable in both, right? So this ampho prefix is referring to 2 different situations, so it can act as an acid or a base. I really should look up the actual definition of that. If we take this equation, which one? This one. So if I take this equation, notice this has a double-headed arrow on it, and I just swap the reactants and products. I just write it backwards. I've got this now. Here I've got NH4 plus OH minus, again with the double-headed arrows, and over here NH3 and H2O. Just wrote it backwards. Now this NH4 plus can act as an acid and donate that proton to the hydroxide ion. All it's doing is it's giving back the baby. But now it's this parent is accepting the baby. The one that accepts the proton is the base. The one that donates the proton is the acid. So this acted as a base, accepting the proton, and this is the acid. These two are related to each other. They're called a conjugate acid-base pair. They go together. They're an acid-base pair. One is an acid, one is a base. And the only difference is that one has a hydrogen ion and the other does not. So a conjugate acid-base pair, any two substances related to each other by the transfer of a proton. So H2O and OH minus. What's the difference between those two formulas? One has an H plus and the other doesn't. That's a conjugate acid-base pair. H2O and H3O plus. The difference is one hydrogen ion. NH3 and NH4. The difference in the formula is that one has an extra hydrogen ion. So this has a charge that's one more positive than this, and it's got one more hydrogen. This has one more hydrogen than the H2O, and it's got a charge that's one more positive. Here, this is the one that has the extra hydrogen compared to this one, and its charge is one more. It went from -1 to 0. So the base accepts the proton, and when it does so, it becomes a conjugate acid. Because now it's holding the hydrogen ion, it could donate that to something else. So when the base accepts the proton, it becomes an acid. It's the conjugate acid. And the reverse. When an acid donates the proton, it becomes a conjugate base. So in a reaction between an acid and a base, here you have the base and the acid, and then in the products, you have the conjugate acid and base. And you can tell what the pairs are by looking at the formulas and picking the two that are the closest to each other. NH3 is closer to the NH4 plus than it is to the OH. You have to do a lot of things to make NH3 into OH minus. So obviously it's the NH4 plus that goes with this one. Those are the pair. H2O is a pair with the OH minus. And here we have it with space-filling models. So to go from NH3 to the base to the conjugate acid, we add a hydrogen ion. To go from water, the acid, to its conjugate base, we remove a hydrogen ion. Where did the hydrogen ion go? It got added to the ammonia. Okay? Just like with oxidation and reduction, in order for oxidation or reduction to happen, the other has to be there as well, because an electron has to go from one thing to another. There's no electron bank, there's no hydrogen ion bank. And you can't just leave them laying around on the sidewalk. They have to be handed off to someone else. Any questions? Okay. This is the sort of thing that could be on a test. Identify the acid, the base, the conjugate acid, and the conjugate base in each of these reactions. I am not going to quiz you on the details of the difference between an Arrhenius acid and a Bronsted-Lowry acid. As far as this class is concerned, it's going to be an acid by either definition, but we should be able to do something like this. So regardless of, start over. The acid and the base are going to be the reactants, and the conjugates are going to be the products. Okay, so what we're going to do here is we're going to look and see which one of these lost a hydrogen ion. Well, this one's C5H5N, C5H5NH. Well, that didn't lose a hydrogen ion, that gained one, didn't it? Here's H2O and OH. This only has one hydrogen. So the H2O lost the acid. It donated it. So that's the acid. So this is our acid. And this is the substance that accepted it. It's babysitting. That's the base. The acid's the one that is going to lose the hydrogen ion. And then we can tell by the similarity in formulas that this is a pair of this one. If this is the base, then this must be the conjugate acid. Because now this one has a hydrogen ion, it could give back. And when it does that, it acts as an acid. So this is the conjugate base, the conjugate acid. Can't spell today. Conjugate acid. I cleaned my screen, and I think I cleaned it too well. I think it actually works better with that film of potato chip grease on it. Conjugate, conga line maybe? Conjugate. This is the conjugate base. Any questions? Let's look at the next one. Which one of these is the acid, HNO3 or H2O? The HNO3 is the acid. Well, how do we know that? Well, you might recognize it as an acid just from its formula. But if we look at that one and we look at the two possibilities over here, we see that NO3 minus is the one that obviously goes with this one because they're the most similar. This has a hydrogen, this doesn't. That tells me that this lost its hydrogen. It donated a proton. So this is the acid. Where did the proton go? It went to this one. So H2O became H3O plus. So this is the base. The conjugates are always on the product side. So this is the conjugate base. And this is the conjugate acid. Any questions?